Great. So, hello, my name is Rinat Shagisultanov. I'm VP of Modern Dev and Application Services at InfoMagnus and ELISA Ambassador. In this session, I focus on the following topic: how to achieve continuous compliance for safety-critical systems that rely heavily on open source software. I will walk through three concrete elements. First, safety annotated software bill of materials based on SPDX3 and the emerging safety profile, used as the backbone of functionality on functional safety traceability. Second, we'll talk about the open continuous compliance or OpenCC platform, which consumes this SBOMs and performs change impact analysis and audit logging. Third, how this approach fits into the support and supports the ELISA ecosystem. The goal is to show a working approach that can run at CI/CD speed, preserves traceability required by standards such as ISO 26262 and IEC 61508, and is compatible with ELISA projects and tools. I will keep the focus on the concrete data structures, relationships, and pipeline stages that this community can reuse and extend. As well, I'll share the actual numbers and results that we are currently observing in the continuous compliance framework. Modern systems today use between 70 and 90% open source components. This is reality across many industries and product lines. At the same time, most safety processes and tools were designed for a very different world: closed development, waterfall life cycles, controlled supply chains, and relatively infrequent change. This mismatch creates what I call the open source safety paradox. Development teams adopt open source to move faster and reuse more. Safety and compliance processes still assume slow, linear change and small known set of suppliers. When these two worlds meet, small code or dependency change can trigger very large amounts of manual safety work. The result is that innovation bottleneck that slows both compliance and development. It does not improve safety. It just increases friction and cycle time. Continuous compliance, in the sense that I use it here, is a way to resolve this paradox by making safety and compliance activities run at the same cadence as the code changes without relaxing standards. The paradox is not theoretical. It shows in the concrete industries. In the automotive, production vehicles run Linux and other open source components at the heart of infotainment, advanced driver assist, and increasingly at high criticality domains. In aerospace, Linux and open source stacks appear in flight and ground systems. In medtech devices, many manufacturers are either already on Linux platforms or planning to transition. In industrial and IoT, large majority of deployed devices rely on open source firmware, operating system, and middleware. The line at the bottom of the slide is very important. Standards such as ISO 2622, IEC 61508, and related functional safety and regulatory frameworks still apply. Open source does not remove this obligation. The consequence of this is straightforward. Safety and compliance workflows must evolve so that they can handle the velocity and distribution of open source development, while still delivering the evidence, traceability, and assurance demanded by these standards. So let's discuss how open continuous compliance work fits into the ELISA and SPDX landscape. At the foundation sits SPDX3, and in particular, it is a safety profile under development. That profile defines how to represent safety-relevant information and relationships inside the SBOM. This includes safety goals, requirements, hazards, mitigations, tests, and evidence. To the side, ELISA projects and tooling includes efforts such as Basil, that was presented by Luigi, produce models, analysis, and evidence that can be expressed in SPDX with the safety profile. They are producers and consumers of safety annotated SBOMs data. On top, The open continuous compliance platform consumes and integrates those SBOMs. It implements compliance automation, performs diff and impact analysis, and provides dashboards and reporting targets at safety and compliance stakeholders. The separation of concerns is important. SPDX and ELISA define the data structures, semantics, and reference workflows. The platform is one implementation that reads those structures and executes automated checks. Any other tool that understands the same SBOMs and profiles can play that role. Here I focus on a safety annotated SBOM itself. Traditional SBOM is an inventory of software packages and files. For functional safety, it is not sufficient. We extend the SBOM model with the safety semantics. Components carry safety classifications such as ASIL levels or equivalent integrity levels. Requirements, hazards, safety goals, design artifacts, test cases, and evidence artifacts are modeled as the first SBOM elements. Relationship then connect these elements. Component implements a safety requirement, a test verifies a particular safety goal, an evidence artifact justifies that a requirement has been met. A hazard is mitigated by a set of functions and architectural decisions. All of this is encoded using SPDX3 and its safety profile. That means it is not an ad hoc proprietary scheme. It's a standard, shareable representation that ELISA tools, external tools, and open continuous compliance platform can all understand and exchange. Here we connect the safety annotated SBOM to the V model. On the left side of the V, you have safety goals and requirements. In the middle, you have architectural and detailed designs and implementation artifacts. On the right side of the V, you have verification, validation, and evidence. We model each of these items as SPDX element and connect them with explicit relationships. Relationships such as implements, derive for, and others express standard engineering traceability. Safety-specific relationships such as safety specification for, safety requirements for, connect elements to safety goals and requirements. The result is a single traceability graph instead of multiple spreadsheets, documents, and tool exports that must be manually aligned. We have effectively one machine-readable model. This graph can be queried, analyzed, and used as the basis for automated change impact and policy evaluations. The previous talk was for Luigi, and here we are. We use Basil, which is the open source software quality management tool that let us define the critical relationships mentioned in the previously. It turns scattered safety artifacts into a live SPDX-compatible knowledge graph, exactly the fuel that continuous compliance pipeline needs to automate proof and keep release audit ready. So Basil does many things. We specifically focus on 4 of them. First of all, we use it as considered to be a single source of traceability. This includes Web UI plus REST API that let teams map and visualize every FUSE artifact relationship in one place. This includes requirements, tests, hazards, justifications, etc. Number 2, it's built-in gap and completeness analytics. Basil show % coverage, highlights missing links, and updates impact analysis whenever requirement or test changes. Number 3, it's test execution awareness. Integrates with CI/CD pipelines and test runners to pull results back into the trace model. And number 4, SPDX Model 3 support. One-click or API call produces a design-level SBOM with all trace links, which is a perfect machine-readable evidence for downstream checks. Why Basil matters for continuous compliance? In every CI run, we can call Basil's API to export the fresh SPDX3 SBOM with safety annotations. And our continuous compliance platform ingests SBOMs, applies FUSA policies, and decides to pass or block deployments. Let's contrast the manual impact analysis with automated approach. In the traditional model, a component changes. Safety engineer or a team then spends days tracing dependencies, checking which requirements and safety goals may be affected, and deciding which analysis and tests must be repeated. This work is meticulous, largely manual, and difficult to reproduce consistently. In the automated model, we treat each release or build as an SBOM. SBOM version is version 1 and SBOM version 2 are compared using the semantic diff. From that diff, we identify exactly which components and relationships changed. We then run queries over the traceability graph. If a changed component is ASIL-D and linked to a specific safety goal, the system traces that link. It identifies any associated hazards analysis, such as FMEA entries and any linked test suites. Those are automatically flagged as required reevaluation or reexecution. This is what SPDX diff and SPDX impact implement. These are components of the continuous compliance platform that combine SBOM versioning, automated semantic diffing, and multi-hop traceability queries to reduce manual effort and increase consistency in change impact analysis. Let's talk about the impact analysis in the process sense. And that is used as a compliance gate in the CI/CD pipeline. The pipeline stages are straightforward. A change is committed, the system builds the software, the SBOM generation runs as part of the build. We then perform the SBOM diff between the previous and current builds. On top of that diff, we run a policy check. Depending on the results, deployment either proceeds or is blocked. Policies are rules defined over the SBOM content and are the associated safety metadata. For example, a policy can require that any change affecting ASIL-D component must trigger associated tests and evidence updates before deployment. Another policy can state that no release is allowed while a safety requirement has invalidated or missing evidence. By placing these policies in the pipeline and driving them from SBOM data, compliance ceases to be a periodic manual review activity, and it becomes a set of explicit automated checks that run on every relevant change. And it uses the same shared safety model across the board. We discussed some key enablers of continuous compliance. Right now, I suggest to step back and look at the bigger picture. These are the foundational building blocks that can turn compliance from a periodic manual headache into a continuous automated signal that flows with every commit. First of all, it's safety annotated and version SBOMs. Everything starts with a software bill of materials that isn't just a flat ingredients list. We enrich each component with functional safety metadata, ASIL, safety mechanisms, evidence links, and we version the SBOM the same way we version code. That gives us an automated time-stamped snapshot of every release or CI run. Second, it's FUSA traceability graph. Next, we express the classic V-model traceability, which means requirements, design, implementation, tests, as a graph that lives inside the SBOM. Nodes are artifacts. Edges are trace links. Graph queries let us answer, show me all code paths that satisfy ISO 262-4 clause 5.4 instantly. The SBOM diff and impact analysis engine is the heart of the continuous compliance. When a pull request lands, we diff the current SBOM against the previous one. The engine flags only the delta. new packages, updated versions, deleted files. It assesses safety impact. For example, a changed MCU driver touching a high ASIL path, and it triggers just the test and evidence regeneration we need. Policy and test automation engine. The policies such as no GPL3 is in the bootloader are codified as rules. The engine evaluates them on every build, and if a rule fails to auto-generates the test case or compliance check required, integrating your existing tests in framework. Orchestration engine is a conductor. It sequences SBOM generation, diff, policy checks, and evidence collection inside the CI/CD pipeline. Could be GitHub Actions, GitLab, Jenkins, wherever you use, so that the compliance stays in lockstep with the DevOps. Integration hooks. We integrate directly with the CI/CD systems to automate SBOM ingestion and compliance gating. Bidirectional sync between the ALM and issue trackers ensures traceability flows both ways. With REST API, CLI level tools, and outbound webhooks, team can automate and monitor compliance in real time. Finally, reporting analytics. Dashboards surface live compliance status, coverage gaps, rule violations, traceability completeness. Because we have versioned SBOMs, we can then trend matrix over time. Great for audits and demonstrating continuous improvements. With these 7 capabilities working together, compliance becomes a first-class automated outcome of every development rather than a fire drill at release time. So at the current Alpha 1 state, 3 tools are central. The first tool, SPDX diff. It performs high-performance semantic comparison of SBOMs. It is aware of JSON-LD context and iRise, which means that it compares the structure and meaning of the SBOM elements rather than just the text fields. I want to stress out that we're not doing the file diffing. We're doing the semantic diffing of the knowledge graphs. It supports all SPDX 3 profiles and can be extended to support custom SPDX extensions. The second tool, it's the SPDX Impact. It performs multi-domain compliance analysis across safety, security, and privacy. It uses the traceability graph and policy rules to determine which evidence has been invalidated by a change and which tests must be re-executed. It also follows transitive dependency chains, so indirect impacts are not missed. The policy agent is YAML-based, highly configurable, and extendable. The third component is CC Audit. It records regulatory-ready audit logs. It uses cryptographic hash chains to make logs tamper-evident, tracks inputs, environment, and outputs with checksums, and supports deterministic execution models so that results can be reproduced. It also integrates with security monitoring systems such as CM platforms. Together, these 3 tools implement the diff, impact, and audit portions of the continuous compliance pipelines. These tools are all CLI, which means that they can run both locally as well as can be integrated with the workflow automation tools, CI/CD tools, without extra layer of dependencies. To validate the approach at realistic scale, we synthesized a complete autonomous vehicle system and generated SBOMs for it. So the system models covers 12 subsystems today. This includes perception with camera, LiDAR, radar, and ASIL-D classification, localization using GPS, IMU, and SLAM, route, behavioral, and motion planning, and so on and so forth. That you see, the components you see here are on this list. For this system, we generated 3 large SBOMs. A design SBOM captures the safety requirement, design artifacts, tests, and evidence. A baseline build SBOM captures 1 software version. And the target build SBOM captures a subsequent version with changes. These 3 SBOMs are large, with hundreds of thousands of elements and millions of relationships. They exercise the traceability, diff, impact, and audit logic at a scale compatible to industrial systems, not just the two examples. And in order to demonstrate the level of the scale of the work that is currently being handled by the tool, let's look at the fragment of the report in the next. This slide summarizes the performance results by running SPDX diff and SPDX impact on the autonomous vehicle SBOMs that I mentioned earlier. The tool dataset includes several gigabytes of SBOM data across design, baseline, and target builds, with over 1 million elements and many millions in relationships. The pipeline processes this data end-to-end in a matter of minutes. SPDX diff compares the baseline and targets SBOMs and produces a semantic diff report. It identifies added, removed, and modified elements and changes in relationships at a throughput which is suitable for integration into continuous integration pipelines. SPDX impact consumes the diff and the traceability graph and evaluates impacts across safety, security, and privacy. It produces counts of total impacts, direct impacts, and transitive impact. And it identifies which evidence items and tests are affected. It also generates structured report and audit logs. The key messages of this slide is that continuous compliance based on safety annotated SBOMs is technically feasible at automotive scale. The tooling can run within the pipeline time, budgets, and handles realistic systems complexity. At the end, I can share with you the actual results from the tool that contains more data about the performance. So what are the next steps currently on the project? First, we plan to build out a full end-to-end use case by integrating these pipelines into the representative CI/CD environments for the suitable project. That will validate not only the performance, but also developer experience and safety workflow integrations. Second, we are actively seeking feedback from the industry stakeholders and the ELISA community on the safety models, SBOM structures, and policy rules used in this approach. The text on the slide calls "this means you" is intentional. The intention is to align this work with the real needs and with ongoing ELISA efforts. Third, we will expand the policy engine, adding more rule features and bundling domain-specific policies, starting with ISO 2622, shaped patterns, and then broadening. Number 4, we will align the SPD with SPDX 3.1 as it finalizes the safety profile and related enhancements. That alignment will keep the SBOM model compatible with the broader SPDX and ELISA tool ecosystem. These steps are short-term and practical, and then can all benefit from collaboration with the community. The midterm goal include the following. Number 1, it's building a dedicated compliance dashboard. This is a web front end that allows teams to configure policies, visualize traceability graphs, inspect impact results, and review audit trails. It gives safety engineers and managers a clear view into the state of compliance over time. Another goal is to add integrations with existing tools. This includes LM and quality management systems, vulnerability and security tools, and commonly used DevOps platforms. The purpose is to connect safety compliance information to the systems teams already use, so that SBOMs, analysis, and evidence do not live in isolation. The further goal is to expand the range of policies and compliance domains. The same SBOM-centric approach can support not only functional safety, but also security and privacy requirements, with dedicated policy bundles for each. Throughout these midterm goals, the intent remains consistent. The underlying models, profiles, and reference pipelines should be open and aligned with ELISA and SPDX work so that multiple implementations can use them. Frontier becomes accessible once the SBOM's traceability audit foundations are in place. One direction is a developer copilot for safety. This would provide real-time guidance in the IDE, suggesting code and design choices that respect MISRA rules and project-specific safety constraints using the same safety models represented in the SBOM. The MCP and A2A supported integrations will enable agent with a human-in-the-loop scenarios. Another direction is predictive risk assessment. Models trained on historical changes, defects, coverage, and incident data can highlight components and subsystems with elevated safety and compliance risks, helping teams to prioritize analysis and testing. The third direction is automated traceability discovery. AI techniques can redesign documents, source code, and test descriptions and propose trace links into the SBOM graphs, which humans then review and accept. Finally, a natural language policy engine would allow safety experts to express rules in plain language that are compiled into the formal policy definitions. For example, a rule that filters all ASIL-D components with failing tests expressed in human language but enforced mechanically. All of these ideas rely on the structured SBOMs and audit infrastructure described earlier in this talk. I will close up with a simple summary. Safety annotated SBOMs give us a unified, machine-readable traceability model for safety-critical systems. Semantic diff and impact analysis tools such as SPDX diff and SPDX impact allows us to understand the effect of changes in that model. The tamper evident and logging ensures that the entire process is transparent, reproducible, and suitable for regulatory scrutiny. Together, these elements enable continuous compliance. Compliance moves from a manual, periodic activity to an automated CI/CD-driven process that runs on same speed as the code changes while preserving functional safety assurances. Thank you for your attention. Okay.
Thank you, Rinat.
Questions or
Yeah.
comments? So
Yeah, feel free.
yeah, I know we're a little bit over time already.
Feel free to ask the question.
Rinat?
Yeah.
Can you please share again this one slide? I think roughly in the first third where you have these tables.
Relations.
You want to represent SPDX relationships.
Yep. I'll be dropping the files directly right now in the chat, but also I'll be sending them over through the email so that you can use it for the workshop.
If you, I guess, Nicole wants to comment on obviously one item, and I see also Stan nodding his head. So I think there are two people. If you briefly would be able to share on the screen again in the presentation mode, that we just take a short look on the slide. If you have the slides still there somewhere.
Is it Philip? Is it the ask for me or someone else?
Did you just screen share your slides again?
Okay, sure.
Nicole and Stan want to make a comment on one of the slides, I guess.
Yeah, just talk about it.
Okay.
And then somewhere in the beginning, more in the beginning about the SPDX 3.1 part.
The one with the SBOM.
Yeah, the one with
This one?
There's a table
where you have the traceability parts and some like.
Okay, understood. So I'll walk through.
Yeah.
This one.
This one.
So I know there have been this test case for relationships in SPDX 2.3. They look completely different since 3.0 now. And also these requirement description for and verification artifacts of relationships that don't exist, and I think they never existed that way. They're just I would recommend or ask or wish that, so if you just want to be up to date with this stuff, just talk to us from the from SPDX safety group, because we have now the PRs for the release candidate there, but we also have a lot of stuff that we can share with you where you have a graphical representation and we can talk about things, or you can look through things.
But this is exactly what we discussed yesterday, right? So the need for having, so this is what we discussed yesterday, the need for having the test cases, some SPDX.
Yeah, but the relationships are not named that way.
Yeah,
Okay.
Because I think it makes sense then also to use on the long term the names that are out there in 3.1 then.
Do we already have some SPDX identifier?
Yeah. Just we started with
That's
3.1. We started with the previous version of the SPDX, and yes, we are ready to move over into the latest approved version, which is basically stating up the one this is the state of affairs as it stands right now. We definitely plan to do upgrades for the latest SPDX standard.
Yeah, this is definitely nothing 3.x. What you show is 2.3.
They also go in different directions.
Yeah, yeah, but that's
Okay.
then the directions are also different now, but that's then cosmetics. Once you touch it.
Cool.
And yeah, just the offer again, Friday, 6 p.m. European time. Show up once in a while, you get an update.
And the full update on SPDX 3.0.
Yeah, so tomorrow I'll talk about the release candidate for 3.1 and let's say an outlook what I want to have in 3.2. And it looks like, yeah, I really would wish that getting more contributions on this Friday call of people that obviously know what they are doing.
Understood. Agreed.
really
We'll definitely increase collaboration, and I'll make sure that Troy Sabin, a colleague of mine, and I, both of us, are present in the working sessions.
It's so fantastic. Thank you.
Thank you, and I think this is a good closure for the session. I'll let run like 5 minutes more, and I hope, Matt, that you will excuse it.